right, so coming up next, now introducing Arthur Daniels, folks, to talk about the perfect index at GroupBy. Take it away, Arthur.
Thank you, Brent. All right, so this is my presentation, the perfect index. And to prepare ahead of time, I put all the slides and everything that I'll be talking about on my website. I've got this link here, dba-art.com/groupby-the-perfect-index. I'll have this link up a couple times. You don't need to write it down right now. We talked a little bit about myself before, but I wanted to mention more about myself. So my name is Arthur Daniels. The easiest way to reach me is on Twitter. I have Twitter, it's Arthur Dan SQL. Right now I work as a database administrator. And besides the normal database administration duties, backups, restores, automation, stuff like that, what I really enjoy doing, what I get to spend time doing is tuning SQL Server, and tuning queries in SQL Server, and tuning indexes in SQL Server. So if you go out and you download the slide deck, what I intended to do with this deck is I'm trying to give the information that you'd need if you had a query and you were thinking to yourself, this query could use some tuning, or I can't tune it at all, but I need to make sure that I have the right indexes in place to make this query really blazingly fast. And I wanted to give you the information so you could make that decision, because a lot of times I'll see developers or people who are stuck with a slow query, maybe it's a report writer, and they'll go, can an index be added here? Maybe they'll see a missing index hint and they'll go, well, would an index make this page faster? Would it make this query faster? So hopefully by the end of the presentation, I've answered some of those questions. I want to go over how you decide if you want to create an index, and I want to talk about how to decide if the index is right. So when I called this presentation the perfect index, what I wanted to talk about was the idea of an index being perfect for the situation you're in right now. I wanted to talk about the current query you're looking at. Sometimes that query can change, but I wanted to give you the tools and guidelines you need if you're going to be creating an index so you can judge for yourself, is this the right index for my scenario? So when I'm talking about indexes, what I wanted to talk about when it comes to indexes are what are called non-clustered indexes in SQL Server. So on the left here, you've got your table, which is where all your data is stored. It's all stored on these data pages in SQL Server. I want to focus on the non-clustered indexes. So these are copies of the data. We define what data we want to copy over into our non-clustered indexes. And I want to tell you how to know what data to copy over. What will make your query really, really fast? And how do you decide maybe some columns don't belong there? And how do you make that judgment call? So let's talk about indexing. And in this session, I've kind of split it up into 3 parts. A lot of what I'll focus on will be things that can make your index tuning easier. So to do that, we're going to work through some examples of indexing simple queries. Now, some of these queries are going to be really overly simplified, but I've tried to pick examples of some more complicated queries that you can see when you're looking at SQL Server, so you understand how different tables or different indexes interact when you're querying like a large, complicated query inside your SQL Server. Then I'll be talking about creating the right index when you have optional parameters. So I see this more and more. Either someone's got dynamic SQL that they've written, where sometimes the where clause changes, or they're dealing with a scenario like they've got LINQ to SQL or another ORM tool that generates dynamic SQL from the application. And those scenarios, what columns are being queried, what columns are being returned can change dramatically. So I'll talk about how to index for those scenarios. And then finally, I'll talk about reasons to not index columns. So in the start, I'm giving you a lot of reasons to index. And then I kind of want to walk it back and give you reasons maybe we shouldn't be indexing. Maybe indexing is not the right answer, or there's not really a good solution for the scenario you're in. So let's get started by talking about the create non-clustered index statement. So we've got our table, and it's got all the columns inside our table. And we want to create a non-clustered index on top of that. And this is just the syntax. I don't want to spend too much time on syntax. What I want to point out to you are the areas that we can define our non-clustered index. So you have to create non-clustered index, you give it a name, you define the table you want to create your non-clustered index on. Then you define what are called the key columns, and then you include what are called the included columns. These are the 2 most important parts, and they have some very significant differences. So where you put the column in your index matters a lot. especially if your query will be changing, and we'll talk about that, why you might want to change where a column is, whether it's inside the included columns or inside the key columns. So if you wanted to get started and you want to create one of these indexes, you should really start with the query that you come from, the query that made you think that things are slow, that you need to create an index for your query. What you need to do then is you need to assess, hey, what columns is my query requesting? What is it filtering on? And what we're going to use is the term predicates a lot of the time. Usually that's just your where clause, your joins, things that can eliminate or exclude data or include data from your query. We're going to focus on what filters are being applied and then determine what data is needed to return to the application. That's how we can determine what will go in our key and included columns, by reviewing what the query is really asking for. So the example I'll be using today when we're talking about these key and included columns is I'm using stuff from the Stack Overflow database. Now I'm only going to be using 2 tables to keep things really simple, but these tables have a lot of columns in them. So I'm selecting to show you some of the bare essentials, some of the things that you really need if you're going to understand the Stack Overflow schema. So when you're a user and you create an account in Stack Overflow, you're creating a new record in the users table. Then you decide on your display name, you type in the location, and when you start out in Stack Overflow, you have very low reputation. But what happens is, as you're posting things to Stack Overflow, as you're answering questions or giving questions yourself, you're asking them, you're going to accumulate reputation. Well, that reputation comes from the posts table, where you're posting these questions and answers. And each post has a score. So if you wanted to know, let's say for me, if I wanted to look at my total reputation and then look at the table where that reputation came from, look at those posts, I would be going from the users table and I would join on the owner user ID. That's the owner of the post. And I would look for the score of that post to see how I scored on that post, whether I was downvoted or upvoted, what people thought of my answers. So I'll show you some examples with these, but I wanted to make it clear this schema, you can query between the users and post table, and you can join between those on different columns. What I want to focus on is joining between the user's ID to the owner user ID. We're finding the owners of the posts. So let's start looking at queries. Let's look at an example of a problem query. And what I've done here is pretty much what I described in the last slide. I've got a query. I'm looking at the users table where I'm retrieving the reputation. I'm looking at the post table where I'm retrieving the score of the post. I'm joining the 2 together on the owner user ID, and I'm going to be filtering for this user. So if you don't create a display name in Stack Overflow, you're kind of given a random username. It starts with user and then it's got some numbers behind it. I picked this specific user because I know about the information behind here. I know how many posts this user has, and I know the reputation, so I could create this example query. But really, this could be for any parameter. You could change the display name. We'll just use that for our example because we want to assess this query, and we want to decide, are the existing indexes good enough, if there are any, and how do we create good indexes for this query? So let's talk about that. Now that we've kind of taken a look at the query, let's go back to the key columns and let's talk about how you could decide your key columns for this query. When you want to keep in mind when you're creating your key columns is that key columns are sorted. They're sorted first by the first key column, then by the second key column, then by the third key column, and so on and so forth. In that way, they're almost layered. If you're going to be accessing this index, you need to access the first column of the key columns. Otherwise, you can't seek to that index. You're going to have to scan the other key columns in the index. And I'll show you an example of that later. Right now, we'll just focus on having a single key column. And that comes into play when we're talking about the last part of the slide. We're talking about making data access easy. When you want to make data access easy, we want to index the predicates that we're looking at, the filters that we're filtering our query on. Now, included columns can cover the needs of our select statement. They can do some other things that I'll talk about later. But for this example, let's just use the included columns to meet the requirements of the select query we're running. So let's take a look here at the 2 parts of this query. I've split it up into these 2 logical parts. Starting on the left side, where we're looking at the reputation from the users table, where the user's display name is equal to that user number that I showed earlier. The second logical part is then joining on that owner user ID to the post table and retrieving the score of all the posts from this user. So when we're looking at this, we can't just create one index because an index can only be on a single table. We really need two indexes to solve this problem. So let's take a look at how these queries run in our demo, and we'll talk about this, and we'll show how these queries are retrieving the data, how the predicates are being applied, and then we can determine if we do a good or bad job indexing for this query. So let's talk about how we can assess that. And we can assess it using two main tools. I'm going to pick on Statistics.io. So this tool shows us the number of data pages that had to be read for SQL to retrieve the query. That's important for us because more data pages is a lot more work that SQL Server has to retrieve. It's more information being processed to return our query results. What we need to use in coordination with that is we need to look at the execution plan. The execution plan will be able to show us, well, what's going on when it had to do those data page reads? What are the Statistics.io actually talking about within SQL Server? So let's get started with demos. I really want to start looking at this data. So let's run some demos and we'll take a look at this. So the first thing we need to do is we've got the Stack Overflow schema up, and you guys can see this, right? All right, so we'll go in here and we'll look at the actual execution plan from Stack Overflow. And we'll enable the Statistics.io, and we'll go over here to the top and we'll include the actual execution plan. So let's run this query and see what results we get back with no indexes on the table whatsoever. And while we do that, let's split the query up into the two logical parts and see the results that we get from that. So if we go in here and we look at the first logical part, we've removed the part where we're doing the join, we've removed the score, we just want the reputation from the user. When we run this query, we get the user's reputation back, and actually need to include the execution plan here as well. So we'll start off and we'll look at the messages tab to see how many pages had to be read to retrieve this data. So it's telling us it's 7,345 data pages that had to be read. And I'll copy that out here. And let's look at the execution plan to show us what predicates had to be used to retrieve that data for us. So if we go to the execution plan and we look at this index seek, we can go down here on the index seek and look at the predicate that was applied. What I want you to pay attention to is what I'm highlighting here, that we're looking at the Stack Overflow database, we're looking at this display name predicate. So this is kind of the index that we want to create. This will be our key column. Because this is the predicate that SQL Server applied, we know that when we go back to create an index, this needs to be a key column that we're going to use. Then when we look at the bottom here and we see the output list, we want to output the reputation. So this will be our included column. So we'll just create a very simple index to meet the needs of this query. Because we've ran the query without any indexes, we know what logic it wants to apply. We've split it into smaller chunks so we can understand what's happening in the query easier. So let's go back and create that index and see the performance improvements that we got. So if we scroll down here, I'm just going to create a simple index on display name as the key column over here on the left, and then reputation as the included column. So we'll run that query. And now that that's completed, let's rerun the exact same part of the query. This time, when we go to the Messages tab, what I want you to see here is there's three logical reads happening within SQL Server, the part I've highlighted down here at the bottom. So that's immediately an improvement from 7,000 to 3. But let's take a look at the execution plan to see what happened. Now that we've got our new index, SQL Server did an index seek. And if we look at what's happening inside this index seek, if we go down to the bottom, we can see that it now has what's called a seek predicate. So beforehand, and I'll show you this in another example, but beforehand it was applying a predicate to the index scan. Now it's doing a seek predicate. So within this index seek, it was able to seek to the value of display name. And as expected, we have the output of reputation right above that. So this was generally a really efficient index. This was great. Now let's go back to our main query and we'll see what happens if we add in the second part of the join, the second logical step that needs to be done. So I haven't changed anything, I just have the single index, and let's see what the performance looks like when we run this query. So if we run this query and we look at the messages, this time we have a lot different logical reads. We have new logical reads coming in on the post table for 800,000 logical reads. Now the users table is still done efficiently. Now to understand this fuller, we have to go into the execution plan. We have to see what actually happened. But just right off the bat, we know that we're still probably using the right index because of this low number of logical reads. But there's still a problem with the post table, so there's still work to be done. So let's take a look at this execution plan. And we'll go in here and let's ignore the missing index recommendation completely. And we'll just look at this index scan on the post table. So what it's telling us down here is it had to look through the clustered index, unfortunately. It's telling us, hey, it applied a predicate, and this predicate's the owner user ID. But there was no index, or it chose not to use an index. It could be either one. So there's ways to improve this query with indexing. If it had to go to the clustered index, we can try to create an index and see what happens with the results. So let's take a look at this. Let's create a non-clustered index on post owner user ID and include the score column, because that's the one we're selecting. So we run this query and we create the index, and then we'll go run our query again. This is the same full simple query that we had from the start. And when we run our query and we look at the reads, all of a sudden, everything's back to normal or back to a good state. We've got only 3 logical reads for both scenarios. So judging by this, I would say our execution plan has changed. So let's go in there and let's check out that as well. Let's look at the execution plan and look at this index seek that occurred. And down here on the post table, now we have a new seek predicate. So not only is it telling us that it used this object up here at the top, it's saying it used the index that I created, but it also seeked on owner user ID. So we managed to index this query. Now we're down to a total of 6 logical data page reads, just meaning we had to read 6 8-kilobyte pages on SQL Server. But let's take a look at what happened to the original query, since that's probably completed by now. Let's go over to this tab, and it looks like it took about a minute to run. I'm looking in the bottom right here. This was before I created any indexes. And before I created any indexes, it had to do the summary of both logical parts. It had to do 7,000 reads on the users table. It had to do 800,000 reads on the post table. And knowing that there's no indexes at this time, if we go to our execution plan, we can probably predict happened is on both examples, it had to do an index scan. On the users table over here on the left, it did an index scan, and then below it, it did an index scan on the post table. So this is the value in indexing these 2 columns together. And we want to look for things like logical predicates, like when the join occurs, joins have the potential to only include the rows that are specified in the join. So we had to eliminate all the other rows or look for just the rows with this owner user ID. That's why when we provided an index on that, it was a lot more efficient and it was able to run a lot faster. So let's go back and let's take a look at this example, and then we'll work with a more complicated example. So we use statistics.io, we use the execution plan to look at this query. What happens when there's an additional where clause? And actually, before I go into this next part, I want to ask if there's any questions about using these 2 tools, because I'm going to rely on statistics.io or execution plans. Are there any questions over in Slack, Daniel?
I don't think so. A thought that I had was about key lookups, but I'm assuming you'll get to those later.
Yeah, well, you feel free to go ahead and ask it, and I can tell you if it's coming up, or we can include it.
Yeah, so I noticed it uses the clustered index instead of your index because your index didn't cover all the columns you needed. And sometimes SQL Server does a key lookup. And I was just thinking if you want to elaborate on that.
Yeah, absolutely. So in this scenario, if we go back to this example, and if I had, so this was the query before I had created any indexing. If we go over here and we look at the query where we're indexing, SQL Server was able to do index seeks and retrieve all the needed information. But let's say I request something else from the post table. For this example, I'll just request the body of the post, which is the text that you would get when someone creates a post. So looking here, we have this body that's all the post's actual information. And if we go to the execution plan, because this isn't an included column and it's not included in my index that I created, we now have what's called a key lookup. So what happens in a key lookup is SQL Server takes information from this non-clustered index that I created. It uses that to go back to the base table and say, hey, I have this identifier for this row, but I need to know what the information for the body of the post is. So at this point, it has to retrieve this output list of the body. And if you look here, the seek key is actually the clustering index key itself. So this is one example of a key lookup. And I'll show you an example actually a little later on where other predicates other than just the clustering index key are applied in this key lookup. But that's a great question. I don't actually specifically cover what happens if you don't include columns, and this is what will happen. Now,
there is actually, sorry.
Yeah, go ahead. Go ahead.
There is actually a question from Amy. So is it okay to, no, the question is, so it's okay to create a non-clustered index on the same column as the clustered index?
That's right. That's absolutely right. And because it's going to be a subset of data, it's actually going to be smaller than the entire index as long as you define your key and included columns and don't include every single column in the table. A good example of that is, let's say we wanted to count all the IDs in a table, and that's the clustering index key. What I would think would happen is if you create that second index on the clustering index key, since it's a smaller subset of data, it'll have to read less pages and have to do less work to get the results you want. You can create a non-clustered index with any key columns and any included columns there's some limitations that I'll talk on later on, but within reason, you can create almost anything. And I wanted to show here really quickly, when we did the key lookup, we went from reading 3 pages to reading 215. We had to retrieve additional data when that key lookup occurred. I'll show examples of key lookups a little later on, but I didn't cover just selecting a key look or selecting a value that wasn't in the index. So thank you. All right, so let's add a wrinkle to it. We've looked at it just very basic, but what happens if we've got a dynamic query? And for some reason, when I was looking for the owner user ID and the display name, someone wanted to filter out and they only wanted to look at the questions. So what this means is we need to filter on the post type ID of post type ID 1. Now there's a table in Stack Overflow. It's a list of the post types. There's about 5 post types. But for the sake of simplicity, we're just going to stick to these 2 tables. And this time we want to filter on the post type ID. So let's talk about how we can index for this scenario where there's kind of an optional parameter that someone's adding in, where occasionally they just want questions, but occasionally they want all the answers. So let's go back to our demos and we'll take a look at this, and we'll leave the existing indexes in place for this demo. For some of them, I'll be dropping them. But for this example, let's leave it in place. And let's run this query that I just showed you. We'll retrieve the actual execution plan, and we're filtering on post type ID. So when we run our query and we go to our messages tab first, we can see the pages read, and we're looking at that 215 pages read again. Now the users table wasn't impacted by this, but if we look at the execution plan to see where those extra 215 page reads come from, we can see that information. So we have the 2 index seeks that we expected to see. And then down here at the bottom at the key lookup, what we see is there's actually a non-seek predicate. What I was just talking about inside a key lookup is there's actually an additional predicate being applied. It's once it's found those IDs, so it does this seek first, and it finds the posts that match the IDs that you're looking for, but it's found more than it needs. And we can tell that because the number of rows read up here is 53, but the number of rows returned, the actual number of rows is 48. So given some basic math, that's 5 other posts that we didn't read. Well, those are either answers to other people's posts or things that users posted that aren't questions or answers. So what we need to do in this scenario is we need to consider how can we remove this predicate from the key lookup, because it's obviously increased our page reads. By requesting 215 pages rather than 3, we're doing extra work. And if we were scaling up our data over time, if we just kept adding pages, you know, a 215 to 3 ratio is really bad. As the more pages we get in that table, the more work is going to have to be done. So let's create a covering index for that scenario. Let's cover this post type ID as well. Now what you could do is you could try either order here. You could try with post type ID first, or you could try with owner user ID first. Now in my index here, I'm selecting owner user ID first, and then I'm doing post type ID. The reason I'm doing that is this execution plan started at the users table, and it found just the row for that one user. Then it went to the post table, where it retrieved the information based on that owner user ID, and it limited it down to 53 rows. So I want to search after I've done that initial elimination down to 53. And this is kind of using selectivity, which is a concept I'll talk about in a little bit. But try it out either way on your own systems. Try it out and see which one is being used first, or which one is being used more efficiently. What you can also think about when you're indexing this scenario is, if one of them is an optional parameter, should it go first in the key values or second? And I'll show that in a really good example later on. But for now, I just want to create this index on the post table. So we'll give that a second to complete. And once that's done, we'll run our query again. And we want to make sure we have our actual execution plan on. We'll run our query, and we'll look immediately at the reads. So we're back to that good number of reads. So if this was a scenario where post type ID was an optional parameter or dynamic, I would want it second after the parameters that I can rely on, which was joining the table. And we're seeing that immediately improved inside our statistics IO. But let's take a look at the execution plan to make sure that we got rid of that key lookup. We got rid of that extra work. And we go back to our execution plan, and we look at the host index seek, and we go down here to the bottom. What I want to show you is these seek predicates. The seek predicate on owner user ID and on post type ID were applied to sort through this data. So this is where reading the query and understanding what it's going to be requesting really helps. And it helps us understand what order to put the key columns in and why to have columns inside the key columns of our index. So let's talk about some other problem queries, and we'll go back. But if anyone has any questions on creating this scenario where you have to have multiple filters, and one filter's in your join and another filter's in your where, which is a scenario I see fairly often, or any other questions, please feel free to ask.
Basil says, no, we can also use where, parenthesis, filtering predicate, in non-clustered index for columns with small amount of distinct values. So I'm guessing he's on to selectivity, which you're going to talk about later, like post type ID in this example. Yeah,
that's great. The other thing I don't want to know is if he's talking about filtered indexes, because if he's talking about a filtered index, that can add some additional wrinkles. And because of their complication, I'm not going to cover filtered indexes today. But if we have some extra time at the end, that'd be a great time to talk about filtered indexes and how they play into your general indexing strategy here.
Also, so, Matt says, sorry?
Yeah, go ahead. No, go ahead.
Matt says, is there a guidance for a number of pages we should shoot for, low number, ratio, etc.?
That's a great question. So it really, this is a hard one to answer without seeing your environment. Now, in this example, I'm running with a very small database. I think it's under 10 gig. So the pages that I want to see read are very low, but it depends on the importance of the query. So think about, does this query need to run a lot? Does it need to run very frequently? And think about how many pages are in the total index. So in the first example, I was showing that it had 7,000 page reads on the users table. If you had a table that had millions of pages, maybe 1,000 reads isn't such a big deal. So it depends on the scale of data you're talking about and the importance of the query to determine how many page reads is a good number for your index. Anything else?
We're all caught up.
All right, great.
They're having a little nerd fight in the Slack channel, but never mind them. The trolls.
Well, good. All right. So let's talk about another problem query. So we've kind of covered, what I've tried to cover so far is creating a covering index where you know the predicates and where they come in a certain order that you can split out logically. In this scenario, I want to talk about a problem query where all the values, there's no joining to another table, we're just looking at the users table, and we're looking for where equals all the values. We're looking for the reputation of all users who live in the United States, who are 34 years old, and have the display name Chris. Now we want to be careful with this one, because when we talk about the display name Chris, as a display name, it's not unique. There can be more than one value for the user Chris. So how do we decide what order to create our indexes in for this? How do we decide the right key order for this index? And we need to understand selectivity to do that. The secret to picking these column orders is the idea of selectivity. So what we need to know when something's selective, is it unique on every single row? A good example of that is an ID or an internal account number. Hopefully we aren't storing real people's like financial account numbers, but hopefully it's an account number for our system or a display name. Something like that, where it's unique on every single row, is a great example of a highly selective value. When SQL Server looks for this value, it can only find one or very few rows. Examples of things that aren't selective on the other end of the spectrum. Well, United States. I was filtering for users that said they lived in the United States. There's over 300 million people living in the United States. Now, they don't all have Stack Overflow accounts, but they could. So that's very lowly selective, or not very selective at all. Same with state, or in the example I was showing, post type. A good way of thinking about it is, if multiple people can identify with a column, if multiple people belong to the same company, belong to the same post type, that's not very selective. But here's the wrinkle on this. If you have a query that's changing, you have to be careful with picking the key column order on the rows that you can guarantee to be in the query. And I'll show you an example where that can go wrong. But first, let's create an index for our query. Let's create an index in order of selective values. So let's go into a demo here and look at these queries and look at the data that I'm looking at with location, age, and display name. So to do that, what I've done is I've counted the distinct values for us. Let's look at the distinct values for the age, the location, and the display name that we're looking for in the users table. So there's 86 distinct ages. That's pretty good. You know, the high end, I think the longest a human's lived is maybe 120, 130 years. So unless they're counting half years or decimals, as long as these are integers, I would expect to have at most 120 distinct values for age. When it comes to location, because anyone can fill in any location they want in Stack Overflow, this has the potential to be infinite. But in this static database that I have, where everything's frozen and there's no one creating new accounts daily, there's only 11,000 unique locations down here at the bottom. What about display names? Well, even though you can have duplicate display names, when we look at unique display names, we actually have 200,000 of these. So this would go in order of selectivity. Age is not very selective, location is very selective, and display name is incredibly selective. It's a great first key column value. So let's take a look at a query. Let's go back to that problem query and let's try to create an index for it. So if we start here at the top and we run our query, let me drop my indexes first to make sure we have nothing interfering. All right, great. So we'll run this query and let's look for this location, age, and display name conditions. And actually, I'll include the execution plan. So because there's multiple display names for Chris, we have 3 values here with 3 reputations. And let's look at the messages tab. Let's see how much work it had to do. Well, with no indexes on the table, with just the clustered index, we have 7,000 total page reads. That's a lot of pages read. That's the entire index. So when we go over to this execution plan, as expected, we have a clustered index scan. But if we didn't know the predicates in our index or in our query, if this was a more complicated query, running this even without creating any indexes helps us understand what is SQL Server searching for. And we can do that when we look in the execution plans at the predicates. We've got the age, the location, and the display name as the predicates. So we know we need an index on these. And we just learned the concept of selectivity. So let's go in here and let's select an index with display name, the most selective first, then location, then age. And just to make it covering so we don't have any key lookups messing with our page reads, I've included reputation. And let's create this index. So it reads all the pages in the index and creates a new index for us. And then let's rerun our query and let's look at the execution plan for that. So when we go to our messages tab, we've improved the logical reads that our query needed. We're down to 4. And then when we look at our execution plan, we see that it was able to use our index. It had to read 3 rows. And we see that all the predicates are contained in the seek predicates. It did a display name search, then it did a location search, then it did an age search, which was really great. You know, once it did that display name search, it had already eliminated it to just the 3 people named Chris because it was such a selective value. But let's talk about, maybe we've got a dynamic query. Maybe we've got an application page where you can type in a display name or you can leave it blank. What happens if that query is generated and they're only looking for users in the United States and the age of 34? Can it still use this index? What if its display name is an optional parameter? Well, we haven't changed our select clause, but let's run this query again and see what happens. Remember, we had 4 logical reads when we were able to use display name. When we execute this query and we go to the logical reads, we've ballooned up to 1,800. Now, keeping in mind, this is in scale to the rest of my database. This is about a 1/7 or in a 1/6 of the entire index that it had to read. So how did it do that? Well, we'll see our answer inside the execution plan. And what we have now is actually an index scan. Because an optional parameter was the first layer of our index and it wasn't provided to the query, SQL Server couldn't get to the other layers of the index. The other key columns are layered underneath that. Now, it can still access them in the form of a scan, and it didn't have to read all the pages, so it's still a fairly efficient operation. It's better than reading the whole table, but we don't have seek predicates any longer. These are just defined as predicates, where it's got a predicate on the age and a predicate on the location. So what would I do in this scenario if I had a query where it's rapidly changing and I know what columns are set and I know what columns are optional? Well, in that kind of case, where we know that we could occasionally include display name, let's create an index with display name as the last key. And the reason I include it as a key is because I don't want SQL Server to have to go read the included pages to find this. If there's a display name that it needs to search for once it's read those 1,000 pages, I want it to be able to find it efficiently. So let's create this index, and we've changed the order. So we no longer have the most selective column first. This is kind of a twist on the idea of selectivity, and this is because queries can change. So we run our query, and let's look at the number of pages read once we run this query to create it. So we look at the messages, and we're down to 6. So this is an interesting twist. I haven't included display name. All I've done is change the order of key columns. It's this exact same data inside the index, but the layers are ordered differently. And because they're ordered differently, now we see a more efficient number of logical reads for the scenario. And if we go to the execution plan and we look at this index seek, we can see that it changed the predicates from being just predicates on a scan to being seek predicates. This is how you could index. You would want to look what's going to be guaranteed requested by the application. Sometimes you can tell maybe we only want to look for a buyer code or something like that. That would be a great first key if you can rely on that parameter always being provided. This is kind of the wrinkle that we get when we have more complicated applications or changing parameters. So I think that's all I have for this demo. What I want to do is I also want to show what happens if you include Chris. So now we've gone back and now we have this parameter again. What we'll do is we'll drop the index that we created at the very start, where we created it on display name first, display name, location, and age. And now that we've just got the second index, the only index on there is the one starting with location and age, but it ends with display name. We run our query again, and we get the same number of great logical reads. It's back to 3. Even though we didn't order it in order of selectivity, this index can cover both scenarios. It can cover optional parameters or required. So that's how I would design an index when I knew that maybe sometimes they're searching for that value. But if you don't have a scenario like this, where maybe you have a fixed set of columns, you can rely on the selectivity to make your index use the columns in the most efficient order possible. So do we have any questions on selectivity or anything like that, Daniel?
Yeah, for starters, you're getting lots of love for being practiced and smooth and very methodical. So there's lots of love in the Slack channel. They've given up their nerd fight now.
Thank you. Yeah. Well, go ahead.
No.
I was just gonna say, if there's any feedback, anything you guys want to give me, feel free to tweet me and I'll check it afterwards. I'll also try to read through the section. And when I show my blog post later, I believe I have a section for comments, and I just love to hear any feedback or thoughts or corrections, even if you guys have anything. So thank you very much for the praise, guys. I appreciate it.
And you also got a tricky question, which you can decide if you want to answer now or later.
Okay.
It's one that I recognize a lot, having worked with BI. If you have a database table with like 1 billion rows, it's a wide table also, and a lot of queries read and search a large number of these columns. We need to limit the number of indexes for best performance, space usage, etc. So the question is, how do you design indexes to be used across multiple queries where different columns are used?
That's a great.
Yeah.
That's a great question. This is not my area of expertise. I deal most of the time with transactional systems where you can have about maybe 5 indexes. And, I'd love to hear your thoughts on it, Daniel. But my first thought would be is that in that kind of scenario, you can actually, I think you can have more indexes in data warehousing type scenarios. So you're able to index more, but I haven't dealt with too many scenarios where it's a really wide table. What do you think, Daniel?
I'm not going to hijack your session.
Okay.
Except to say, column store indexes.
Ooh, great point. Column store. So whoever asked that question, Nico has a great session. I think it was on GroupBy. Lookup.
It says it's actually more. He says it's actually more of an OLTP table.
Oh, interesting. Okay, so if
still,
I had,
I still try to shoot for the column store actually, because the column store isn't sensitive to column ordering. It just includes all the columns, and you can pick and choose which ones you want to use. So try that query.
Yeah, there's a GroupBy session on creating column store indexes, and if you want to create them for transactional systems, I think there's some extra caveats, so you want to be careful. I don't have any experience with those, so I can't actually speak to that.
And it's sensitive to versions as well. It gets better with each SQL Server version, simply put.
Oh, great. Yeah, so first upgrade, right?
Yeah.
All right.
Here are lots of questions. I hope you have the time.
Yeah,
maybe
go for it.
You can tell us how the index is placed in pages, from Anton.
So I'd be curious to know if he's talking about like the physical storage structure or.
I'm assuming yes.
Okay, so I don't want to go too much into physical storage structure simply because I don't necessarily know all the internals of indexing. But when I'm referring to the layers of indexing, that's the physical structure to an extent. Non-clustered indexes use a B tree structure. So that means at the start, you've got the first key column in order, and then on the layer of the B tree below that, you've got the second key column, and so on and so forth. So the physical structure of the index is what's preventing it from being able to use the other parts in an index seek when you removed that first key column as a parameter.
Yeah. So questions are flooding in here. You'll just have to tell me when you want to move on.
Let's do one more and then we'll move on.
All right. So Brian says, and by the way, Corey with the column store thing, he says he's on 2012, so column store is not a great choice. No. Brian asks, if you remove the predicate for display name and leave the other two, will it use the index with the display name as the first key value, perhaps scan or skip altogether?
Yeah, and I think I tried to show that in the demo, but yes, when the data is available in the index, and it's a smaller subset of data than is on the clustered index, SQL Server will often try to find the smallest index possible that still has the data it needs, even if it's not in the right order to do a seek. So yes, it would do a scan in that case.
Yeah. And finally, just one short one. Amy asks why you're including maxstop in your create index statements.
So that's a really great question. Some of that is habit. So I work in a system where we want to specify, we don't want create index statements to go out of control. And it's just really a habit that I've developed. So I just include maxstop when I create my indexes. I didn't mean to imply that should be part of your syntax.
Cool.
Great. So let's move on with the presentation. I think we've still got plenty of time, and we'll try to stop for questions in a little bit. Again, I'm loving. It's really great to hear these questions.
It's really engaging session. It's really cool to see all the questions.
Well, thank you, and thanks guys on Slack. So let's talk about a different problem query. So far we've covered what happens when you do a join, and you've got a join with additional filters, or you've got multiple equivalent columns, and sometimes you remove one of the columns and sometimes you add it back. Let's talk about a problem query where you have different types of predicates. So now we're looking at the same users table, but I want users who created their account between December 2008 and December 2009. I want users who live in the United States. And I want to do a wildcard search. Just show me all the ones with the username like user. So one thing about the Stack Overflow, the whole website, you don't have to create a display name. And if you don't, you end up with a display name that looks like user with some numbers after it. So let's take a look at this problem query. But before we jump into a demo, I want to show you how I would break this down logically if I had this query. What I want to do right off the bat is I want to split this query up into, here's some greater than or less than predicates, here's some equal predicates, and here's some like predicates. So your queries, and some of you have some very complicated queries, but what's important is to identify what's being searched. And we'll throw out the complete option of optional. We'll just consider this as a static query. All of these columns will always be requested by this stored procedure or by this query. So based on that, how do we create an efficient index? Well, let's look through some demos and we'll see what the best index for this kind of scenario is, where we have different types of predicates. We want some information. Maybe the wildcard can search. It's like a user can search in, it's like they're doing a Google search and they type in whatever they want. So let's take a look at the demo and let's look at multiple predicates where different types of predicates are applied. So first I'll make sure that we've cleaned up all our indexes, and then we'll go over here and we'll look at different predicates. So what I want to do is mentally I split it out in the order that someone supplied them. This isn't necessarily the best order. I just want to logically get an idea of what needs to be done for this query. So first we want only users from those creation dates. And we run that query. Let's get the execution plan. We know in the execution plan it's going to do a clustered index scan because I dropped all the other indexes possible. And as expected, it's reading the entire table, 7,000 pages. So let's go down here and let's create an index on creation date, and we'll include reputation. So we've created our index, we'll run it again. And what's cool about this is greater than or less than our indexable columns. When we've created this index, we're able to get an efficient index seek on these values. Creation date, it's a great index key column. It worked for this query. We got a seek predicate, not just a predicate. So I would say this is overall much more efficient. We've created an index for this query. But let's look through the other scenarios. Let's add in the second predicate that we have. This time, we're going to look for the predicate location United States. So we run our query, and we look at the messages tab. Unfortunately, we're back to our logical reads. It's back to reading the entire table. Let's look at that behavior. Oh, it went back to a clustered index scan. And what it's doing is it's applying both predicates in this clustered index scan, which makes sense. I didn't include location as an included or key column. So to get the data, it had to go to the clustered index. So we won't look too much at this missing index request. But what I want to point out is that missing index requests like this can appear when you don't have any indexes in your table, or when SQL Server just doesn't have enough information. So let's create this non-clustered index, but instead of ordering it like the missing index, where they're ordering the location column first, then the creation date second, let's try it with creation date first, because that's the order it's written in, right? Well, let's create that index, and let's rerun that step. We're just rerunning location United States, those users again, and we go to our messages tab. Hey, 344 logical reads. It's a lot better than 7,000. That's a really good amount. Let's look at this execution plan. Let's see how it used our index. And we still have a missing index request, which is kind of interesting. So when we look at our index seek, we want to see that there's actually two operations here. First, not the first operation, but just first in the order that we're seeing it, is this predicate on location. And then the seek predicate that it did before that was on creation date. So judging by this, in this scenario, if I saw something like this after I created an index, I would want to try reordering the predicates in that index. Because what I'm seeing is I want everything, if it's going to be a covering index, if it's going to fit that query specifically, I want everything to fit inside the seek predicates. So let's run that example. Let's try it the other way around. Let's try it with location first and then creation date. So we create that index and then we run our query yet again. We are at 344 logical reads in the previous example. Now when we go to our messages tab, we're down to 11. So the cool thing about this is, if you're testing in an environment where you can create indexes as much as you want and you have good enough data to test on, it doesn't have to be real live data. What you can see is when both indexes are created, SQL Server picked the one that I had created second. And what it picked was this index that I created on location and creation date. And when you look inside the execution plan, this is the crucial step. Now we have all seek predicates. So SQL Server knew the order that it wanted the indexes in, or the key columns in. We just had to try things out, just experiment. When we had indexes as a predicate, not a seek predicate, we had to try things out, see if we could get a better execution plan. So that's guaranteed that we have location, but we haven't added in the third predicate yet, the like clause. So let's add that in and let's see what happens. So we were looking at 11 page reads for our last example. And let's run this again and see what we get. When we go to the messages tab, we've ballooned up. We're at 3,679 logical reads. That's a big difference from 11. And I imagine we'll see something in this execution plan. So let's take a look. Oh, there's our huge cost, right in this key lookup. So in the previous example, it did this seek on location, and then it did a seek on the creation date. But what it had to do was then it had to apply this wildcard. It had to go look for display names that were like user. And that's where a lot of the extra page reads came in. If we look up here in the top of the execution plan, the number of rows read, it read 1,000 rows. So while that's not a lot in this example is scaled down fairly. What I want you to know is when you don't include a column that could be used for searching and SQL Server has to go do a key lookup, this predicate, and the term for it properly is residual predicate, is fairly expensive. This is an expensive example. So knowing that we want location first, because we tested the index and we know that location is going to result in less logical reads, then we want creation date second. How do we index for a wildcard? Well, the stinky thing about wildcards, the thing that really stinks about this, is that wildcards can't be seeked. When you have a wildcard on both sides, I should specify. There's some special cases, and if you have to deal with wildcards a lot, this is something that you should look more into. But if you apply wildcards on both sides of the statement, even if we create this next index and we walk through this next example where we're searching through the same query, what we'll see is we got a better amount of page read. We got 14 instead of 1,000 or 3,000, whatever it was in that last example. But inside our execution plan, we weren't able to move the predicate to being a seek predicate. Now, you're welcome to try this out, try different orders of things. But the thing about a wildcard is it has to look through each one to make sure it's not anywhere in the string. It has to look through the entire set of the string. So it's not going to be able to seek to that value. So you're always going to have this additional predicate. But we reduced the amount of work that it had to do by including it in the key columns. You could also add it as an included column. Now, this is something you'd want to test out. So this is kind of an example of how you can order the predicates. Now, what's important to remember is it's not the order in which you type them in the query. It's going to be the order in which SQL Server chooses to search on them. And it's worth experimenting, layering the key columns differently to see if you can get a more efficient execution plan and if SQL Server can search the things faster. So at this point, that's my multiple predicates demo. Are there any questions on multiple predicates or wildcards or anything like that?
No, just more love for your presentation style. I think people are really thinking you're methodical and let me see. No, it's all just love, no questions.
I appreciate it, guys. I'm looking forward to reading the comments afterwards. Thank you, everyone.
Oh,
so let's.
lots of people are typing. Will you show what happens if you take out the first % sign? Asks Kevin.
Yes, yes. So what time? How much more time do we have? I think we have
It's
another.
10 past the hour, so you're 55 minutes into.
Okay.
Yeah, you can take another 10, 15 minutes if you want.
Okay. So I will do that because I want to show you what happens. So this is kind of a cool case where SQL Server, when you change things around, sometimes it can get more efficient. Now I can't guarantee because I've tried a lot of these demos out and I made sure that the results were the same. I've read some stuff online and I'd encourage you guys to go read more because I'm not an expert in wildcard searching because that's not something I do often. Now, this is not going to be something that's usually efficient in SQL Server, but I know that removing the first wildcard, sometimes SQL Server can search through these first few characters and do that more efficiently. Now, I don't know if I have the tools, but let's see what it did. So unfortunately, it's the same number of logical reads for this example that I've got up right now. If we go to this execution plan, it's still reading the same amount. So this isn't a good example of that.
What was your index definition?
Oh yeah, that's a great question. So my index definition was location first, creation date, then display name.
If you move display name before creation date, that'll work.
Okay. You want it in this order then?
Your session, obviously.
Well, let's give this a try. And if this doesn't work, what I'd love to see is if someone has the blog post. I think there's a couple blog posts about indexing for these wildcard scenarios, or I know there's some information on why you shouldn't do wildcards within SQL Server. But let's take a look at this query and see if you're right. Let's see if we
Our
can.
users demand wildcards, so it's not for us to choose.
That's a great point. So yes, that worked a lot better. Thanks, Daniel. 5 logical reads instead of 14. And if we look here at the index seek, unfortunately now it's doing a creation date predicate. But because it was able to search through those users first, in this example, it was less logical reads. And I can't say too much to how that's effective in other scenarios, but that's a great question, and I learned something too.
So what it does is it converts the wildcard that when you end the wildcard with a percentage, it converts the wildcard to a greater than, smaller than. I think you can see it in the plan even, if memory serves.
Yeah, and that'd be a great thing. Let's talk about that afterwards. I want to show some things that I just talked about and why I did the things that I did. So in this next slide, I wanted to talk about what I was trying to do. So when I was trying to create an index on this table, what I tried to demonstrate was key columns do a few things really well. What they do really well is when you know what the value is, when your parameter is equal to a certain value. They also do greater than or less than 2 equal. They do these really efficiently. These are index seek events. You can seek on these values. The things that they don't do so well on, the things that they can do okay on, and obviously I was shown that they can get better, is they can do like wildcard searches. So what function do included columns do? Well, included columns do some things really well. If there's a value that you want to select and you're selecting that value every single time you query a table, perfect for an included column. That's absolutely amazing. They're also good for being there. And the reason I say being there, let's say you have a dynamic application. Sometimes we want to select some columns, sometimes we want to select another. If you have them included values, you don't have to worry about a key lookup. Now, key lookups aren't the worst thing in the world. You need to understand how much work is being done, how many pages had to be read. But if you want to really cover, if you want every single condition covered, sometimes you have to include them as included columns. And I'll provide a counterpoint to this next. But if you think about it and you need them to always be there, they can always be there as an included column. You can also scan the included columns. So I mentioned very briefly, and I don't have a demo for this, unfortunately, but what can happen is SQL Server will look for the smallest index to use, and it can scan through the included columns on that index. So if you have these very, very, very large tables, but you only have a certain number of rows like locations, even if I have to scan through 11,000 locations, it's still better than reading through every single page on the entire index. So why wouldn't you want to include all these included columns? Well, think about it like this. We've got our post table. And the first index we created was on the owner user ID. And we included the reputation on that. But for the sake of this, just pretend it's an index on a single key column. Think about this in terms of data sizes. Each of these cubes represents more and more data. An index that includes owner user ID is going to take up very little data. Then when I include more information, when I include the tags of that table, we're dealing with a larger index. Let's say we grew from 1 gig to 5 gigs. But if we go crazy, if we decide my query could use anything, I want anything that's possible. Well, in those scenarios, if you include every single column possible, you can end up creating an index that's the same size as your base table. Now, that's a decision that you have to make. That's a trade-off. But I want to provide it as a word of warning. You're creating a lot of overhead, a lot of size inside your database. And unless you really need those columns, unless you need this query to be mission critical fast, it's often a bad idea to just include everything. Usually someone ran a select star and they're saying, well, I need all the columns. Well, you don't necessarily need all the columns. So I'm reaching the end of my presentation, and I want to talk about the main key points that I wanted to include. When you're doing index tuning, you want to start off and you want to interpret the predicates of your query. If you have query tuning skills, apply these ahead of time. Use the information you know about the query and then run it. See how SQL Server interprets your request. See what it wants to use. A lot of what I did to start every single one of my demos was I ran the query and saw how SQL Server used that data or how it searched through the data like it was. Then you want to order your key columns to maximize their usefulness. Sometimes this is in the most selective order, but sometimes if your query is changing or if you want certain things to go before other things in your query, meaning you want account number first or you want location first, make sure that the order of the key columns you've experimented with, you've tried things out to make sure it's the most useful key column order. And finally, include or remove included columns for your scenario. I've seen a lot of effective indexes that have very few or no included columns. It's not a necessity for performance. And like in the example with the data sizes, the more included columns is the more weight. So thank you, everyone. Thanks for all the kind words on Slack. I'm looking forward to hearing some feedback. I have the link up right now. If you want to download, if you don't want to download, I have a link to SlideShare where I've uploaded the slide deck. If you do want to download, I've got the slide deck, I've got the demos, everything's already out there on my website. Feel free to reach out to me. I have LinkedIn, I have all that stuff. The best way is usually Twitter, Arthur Dan SQL. Thank you everyone for attending my session. Thanks for having me here, guys, for GroupBy.
Very nice job, sir. Yeah, you definitely want to read the Slack comments. Tons of people putting in thanks, mind blown, thanks for the talk. Brian made
Awesome.
a very nice presentation. We even had a couple people asking, are you an MVP? And I said, well, because they said you clearly should be given how much you know about the topic. I said, well, here's a link to go nominate him for MVP. There you go.
Wow, I'm blown away, guys. Thank you so much.
You bet.